Okay, now hello everyone. Okay, now we have discussed the arc length before, right? The last discussion. We have learned on how to find the arc length in vector functions. And if you look here at the example, we have the magnitude value of the first derivative, right? And that is actually comes from the the magnitude of the parametric, right? The parametric, the x, y, and z. Okay. So we can actually simplify the parametric one and then make it into the magnitude value of the first derivative. Like here, if we look by these equations that we have learned in chapter 10, yeah, I believe this is quite familiar with you. So it's actually similar approach, and the difference is we now have the three directions: x-axis, y-axis, and z-axis, in which they have all each own their own parametric equations. And the idea is if we would like to derive them, or if we would like to derive the r, then we are going to derive each component, f, g, h, and if you want to find the r prime, it means that we are going to derive f to f prime, g to g prime, and h to h prime. And here it is how it looks like, the formulations, and how we are getting the magnitude value from this arc length, because arc length itself having the square root by itself. So by definition, in terms of the magnitude of the vectors, it's actually equivalent, and we can then transform the normal arc length functions in parametric equations into the magnitude value of the first derivative of the vector functions, okay, as you may see from this one. Okay, as I mentioned before, that when you derive each component, x, y, and z. And also when you integrate, you also integrate each component. For example, integrations f, integration g, integration h, to find the integration of the vector r. And also it's we can also consider the limit, because derivative and integrations, they are all based on limit, right? Okay, so it should be obvious. Okay. So by this section of chapter 13, you should be expected to have been familiar with this terminology, okay, to this definitions, or this techniques, to includes all the techniques from calculus 1 inside the vector functions. Okay, I think can go through, or if we look here, this is how we approach the arc length. Okay, like usual, we incorporate the tangent, in which we can actually observe or analyze what we have been through until we approach the curvature. So from here, actually it has some similar vibes with the curvature that you will find in the next few sections. Okay. I think we can go for the curvature. So the curvature, if you look at the definitions, it's the degree of smoothness. Okay. So when you see a curve that has some rapid change of its directions of tangent, means that it has some degree of smoothness change. Okay, so that's actually what smoothness means. So here I wrote that how rapid the curve is changing with respect to the length. So you see that unit tangent vector, or dt over dt small dt, okay, and over ds over dt here, dt over ds actually. It starts from dt over ds, the unit tangent vector, divided by the parameter of length. S is actually a length. Okay, and we are see here, if we are using the chain rule, and then we can expect it to get the t prime, or unit tangent vector, the first derivative of unit tangent vector, divided by the first derivative of the vector functions. Okay, so by doing so, we are going to observe how fast or how rapid the curve will change, okay, in terms of tangent to the length. Okay, let's continue. So there are a few other formulations for curvature, at least three formulations. Okay, so let me write the first one, that the unit tangent vector is equal the vector function, the derivative of vector functions divided by its magnitude value. Okay, that should be obvious. So from here we can rewrite r prime equal to magnitude, its magnitude multiplied with the unit tangent vector, and we know that this r prime, we can exchange its magnitude with ds over dt from the definitions of from the definition of the first derivative itself. So we can take this into the second derivative. So we are going to take derivative. So we are going to apply the product rule, because ds and t will be in each own functions. Okay. So take the second derivative. So we have a product rule. This is the results. Okay. Now from this r prime and r double prime, okay, what we are going to do next is we are going to cross this. Okay, we are going to cross product the r prime, cross product with the r double prime, and it will be equal to ds over dt. Okay, let me just write all the things that have been written before, and crossing the all the results from the product rule before. Okay, now to cross product, we can deal one by one. So first component and then the second one. Okay, so, and remember we need to cross. Okay, so the notable mention is actually the unit tangent vector. Okay, so we will going to write the first component. So this will result t cross t, which resulting 0. Okay. It's orthogonal. Actually, it's not orthogonal. It's because it's crossing its own line. Okay, so sorry, it's not orthogonal. And then t cross t prime. Okay, since we know that the unit tangent vector, the magnitude is 1, we can write in terms of the dot product that its derivative should be also 1. So from here we can also write that it should be resulting 0. And now we can write down the cross product of r prime and r double prime as r prime squared and magnitude of unit tangent and magnitude of the first derivative of unit tangent. And we can rewrite the first derivative of unit tangent is equal to cross product of r prime and r double prime divided by r prime squared. And we can write curvature as the unit tangent vector divided by the r prime. So we just need to divide with the magnitude of the first derivative of r. Then we can write as r prime cubed like that. So this is another formulations for the curvature. Okay. Okay. We can write a more clear curvature, and this will be one of the essentials for the curvature formula. So I need you to pay attention to this formula, okay? Because we are going to use it for a while for some cases. Okay. Okay. Now let's have an example. So find curvature of the functions rt. We call this the twisted cubic just at the origin. So from this formula, we are just apply and we just need to find the first derivative and the second derivative and just put it on this formula. So first we need to find the first derivative, the second derivative, take the cross product. Okay, take the cross product. So r prime is 1, 2t, 3t squared, and derive once more 0 to 60. And take the cross product. Okay, now we are going to evaluate. and take the magnitude. So it will be 36d4 plus 36d squared plus 4. And the curvature, we can write the curvature as a function of curvature, like a tangent. If you remember the tangent, we will sometimes we need to specify the tangent at some point. So the curvature is so similar. We can specify on the point that is mentioned in the questions. For example, in our example here, we just need to find at the origin. Okay, so the curvature we can write the r prime is 2t squared. Okay, so 1 plus 4t squared plus 9t with power of 4. It should be cubed, but it has square root, so it's 3/2. And then we need to apply when t is equal to 0, which is this is equal to 2. And if you check the chapter 13 exercise, especially the curvature, sometimes the results will have some square root because of the value that you are going to achieve. You have a square root of something. So it's not really an exact formulation for the results. So not like really exact numbers. I usually have it the square root. And we can also apply this curvature on 2 dimensions. With a certain functions, we can apply the same or similar formula here, and we can exchange with our functions. For example, we can exchange the r, use the r having 3 ijk. So whenever you have a function of y, f of x, okay, so for example, have maybe let me write later in the new page. But what I want to say is we can apply the curvature in the plane curve in 2 dimensions. If you have this y and x, we can apply that, and the ijk we just erase the k. So we can apply similarly with this formula. Let me go into the new one. Okay, so for example, for y equal f of x, our usual functions in the calculus 1, right? We can rewrite the r, and instead of another parameter t, we can write x. And we can write the terms for x, I, plus f of xj. So we can also rewrite r in terms of x and f of x. Okay. And simply we can set up our formulations for the curvature with r prime and r double prime, similar with the previous one, but we are exchanging the r with x and f of x. So we can have a differentiate with terms of x. Okay. So this will be I plus f prime x j. Okay. And then r double prime will be just f double prime x of j. Okay. Now remember that if we have I cross j, this will be going to be k, and j cross j will be 0. Okay. So if we have r prime cross r double prime, if you write it in terms of I, j, k, so this will be 1, and then f prime x, and then 0, and then this will be 0, f double prime x, and then this will be 0. You will see that we have now, if we are calculating the formulations, okay, we will just having f double prime, right? So this will be resulting f double prime x. Okay. Okay. And then let me write here that the magnitude value of the first derivative, this will be 1 plus f prime x. Don't forget to square. Okay. So the curvature we can write as the magnitude of f double prime x and then 1 plus this is squared, and then the square root becomes 3/2 because of the cube. So this is another way to write the curvature if you have y equal f of x, okay, in terms of 2 dimensions. Okay, we can also add the notes that if our magnitude value of r prime is a constant, or c constant, then the r prime is orthogonal to rt for all. Okay. This means that every time you have a derivative, okay, for example, you have the t, you have the derivative of that t, which means that this will be orthogonal, and we can write the normal, because since the normal, as the definition, will be the orthogonal factor of the t, so in the concept, in the principle, we can define this as, in terms of unit factor, t prime defined by magnitude value of t prime. Okay, hope that helps. Okay. And now, what is the binomial factor, or b of t? Okay. So binomial factors is perpendicular to t and n. So let's have a short break. Okay, let's continue. By the way, do you aware that some of the students and I think faculty member also a confirmed case for COVID? So I think if you also contracted with the maybe your friends, okay? I think I think lately it's getting increasing the rate. I think to 2,000, right? 2,000 case. But hopefully it's not as severe like last year. I think this year not really that bad or severe the infections. So we still can go for classes. If we perhaps whenever we have maybe online class, whenever something happen in the future, perhaps we will go through either going to using Google Meet or I think WebEx or Microsoft Teams. Yeah, because I think Google Meet is not as powerful as before because of the limitations of the cloud storage now. So yeah. Yeah, and please let me know whenever you have maybe case or confirmed case. Okay, let's continue. So, by definitions, for the binomial vectors, we can write this is T cross N. So from these definitions, from the unit tangent vector, the normal vector, the binormal, so whenever you achieve some directions on your unit tangent vector, you can write down your normal and then also write down the binormal. So if, for example, by these definitions for this cross product, okay, so whenever you have T is here, and maybe this is N, say this is N. So by crossing these two vectors, we will have a vector that is going here. So it's all of these three units, they go for each direction. It seems that you can also imagine in three directions like that. Let me put the graph. And you can imagine the point on the graph, it can be observed through any curve. So the point can be observed here, 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 and it goes by and following the direction of the unit tangent vector. Okay. So we have also go through here. Whenever we have some movement, you see the idea is just the unit tangent. First is unit tangent. So you look at the unit tangent. First, this is the N. Binomial vector is going outside, like that. So move here. The unit tangent goes there, and the unit vector for the normal is also changed a little bit. And this binormal also changing, it's going over outside like that. So the principality to find the all these three begins with this unit tangent. Okay? So that's the first thing you need to take notes. So T will be very important. Okay. Let me go through the example. Okay, let me go through the example. Find T, or let me write in terms of the words: unit tangent, unit normal, and binormal vectors, and curvature of vector functions R at 1, 0, 1. So it's asking T, N, B, and the curvature. To write down, first we can derive the functions. Okay, and then find its magnitude. One plus 2 plus 1 over T. So there's a lot of calculations through the this unit tangent, normal and binormal. So we can take this 1 over T squared. So this will be T4 plus 2T squared plus 1. Then we can take this T squared plus 1 squared. Okay. So we can have this So this will be the magnitude of R prime. And this is also because T squared plus 1 is always positive. So we are just taking the positive one. And now from this R prime, we have the first unit tangent vector. Right. So we can write T squared over T squared plus 1, and the factors will be If we want to find the normal, we can derive first the unit tangent. So we need to have applied product rule. So this will be a little bit complicated, so you need to be careful on all these calculations. So this will be negative 2t over t squared plus 1. That's the first one, plus the other one will be the 1. And then derivative of the factors, this is 2t square root of 2, 0. Okay. Okay. Now we need to evaluate at some point. It's 101. Okay. So because of the r, t is equal to t. So at 101, this will correspond with t equal 1, right? Okay. So our t is equal 1, so we can decide that the t1, we can put on the, this is, t will be, where is t? Half 1 square root of 2 negative 1. Okay, and t prime, this will be negative this will be, sorry, I forgot the square. Negative 1 over 2, 1 square root of 2, negative 1 plus half 2 square root of 2, 0. And from some calculations, we have calculations here. This will be half. 2 minus 1 is 1, 0, 1. Okay. This is t prime 1. And the normal vector will be t prime 1 divided the magnitude. So the vectors divide its value. One plus 0 plus 1. So this will be 1 over square root of 2, factor of 1, 0, and 1. That will be the normal. So this is the unit tangent, unit normal. The last one, or not the last one, the binormal. This is t cross n. So t is half. So we can write t as half square root of 2 and n t cross n is Oh, wrong. -2. Okay, that is correct. So B1 is half 1. And then -1. Okay. And then the curvature is, we can get this from this formula. Okay. Remember that the curvature, we have the curvature in terms of dt over dt small dt and ds over dt. This is equal, okay? And we can write this from the calculations we have. And you can also use the other formula for curvature. It should be the same results. I think it's too complicated for the cross. Actually, you can compute the cross just so t cross n, so half multiplied by 1 squared over 2, and then you can write down t, where's t, 1 and then cross the n, 1 0 1, so 1, and then calculate here. This should be going to be equal, same result should be, or this is square root of 2, -2, negative square root of 2. Okay, so a lot of calculation here, but the key is, I think, as long as you get the correct answer for the unit tangent, when you find the normal and then binormal and the curvature, you will get all the correct result. But if you maybe make some mistake on this tangent here, you will not get everything correct. So be careful on the first step. So here is all the terms for the normal, binormal, and also the curvature. They depends on the unit tangent. And so unit tangent will be very essential. So the next section should be about the plane. The plane and torsion, but I think if we don't have time for the torsions, it should be next Tuesday. Okay, let's continue a little bit. Okay, so if you have T, okay, and you have, for example, another one is the normal vector, N, and you have the other one, the perpendicular to T and N, which is the binormal. Okay. So from these three particular vectors, as we mentioned in chapter 12, that vectors will be related to the plane. So we will have at least two planes. Bn, it has a plane. It has a plane like this. It has a plane. And Tn also has a plane. So we also have another one here. Okay. Now for Bn, so Bn will be we call this is the normal plane. And the Tn will be the osculating plane. So this will be osculating plane. So what's normal plane means? Suggesting by the terms normal that all the plane that is orthogonal to T is called the normal plane. So it can be here, okay. So it can be everywhere where it is orthogonal to the unit tangent. Okay. An osculating plane, okay. Well, we can say the osculating plane will be the orthogonal part of the normal plane. We can say that. Or if you see the name osculating, it's actually translated to kissing or touching the point. Or you can say that it's actually the plane that is containing the curve. Okay. So let's say the curve is we can say equivalent with the tangent. Okay. Let's say the curve is here. The curve is probably here. Okay, based on our definition of the unit tangent vector. So the plane that is on the curve itself is called the osculating plane. We can say that this will be our and imagine if we change the point and the plane also changes. The plane also changes. But we have a definition that on a point we will have two planes that is consists or it's created from the three vectors that we defined before. Okay, and then aside from normal plane, osculating plane, we have also, we call the center of curvature or circle of curvature. So this is called the circle of curvature, or osculating circle. So this is definition of, let me write, circle. So the green one, that is our circle of curvature. So this is circle in the osculating plane. That pass through, that pass through a point, let's say point P, with radius 1 over the curvature. And centered by 1 over curvature from P along the vector n. Okay, now imagine the graph that you have from before, the oscillating plane. You see from one side, and see from where you can see the normal. You can see the normal. So if this is the normal, means that we have a plane right here. We can imagine the terms or the plane itself as a circle. As we move the point, the circle, it has a relation with the curvature. So when you know the curvature is changing, okay, for example, the curvature at this point should be highest, okay, because the radius is going to be reciprocal of the curvature. It has a small circle, so we can imagine it's like small circle. And when we move the point, it will change. It depends on how the curvature will be. And then, for example, here it's the curvature is going bigger, and when it's going nearby the middle one here, it's going smaller and bigger. Okay. So it's also visualizations on how the curvature will look like, or maybe how the curve can have the degree of smoothness. Okay. So it helps you to see from this graph that you can rewrite or take the curvature, okay, into a graph, okay, into a circle. Okay. So before we can design from a simple functions, just like function of x, we can design where the curvature will. But when we have a function that is not described as simple as function of x, maybe in terms of 3 dimensions, like this one is x, maybe 3 dimensions, but we can take its part, and if we can project this into 2 dimensions like this, we can make it into a circle. Okay. Before our class, okay, I know that some of you maybe have trouble or have difficulty to imagine this in terms of what this really looks like and how we can apply this in our real life. I'm not suggesting to maybe go through learning some application, but at least for the curvature, we know how the curvature can be visualized, can be derived, okay, can be developed. So maybe to summarize, at least several things that important. Okay. First is the unit tangent vector, which is defined by, it depends on the first derivative of the vector functions, and the normal, which also depends on the tangent. the unit tangent, okay, because it's also orthogonal. And the binormal, which defined as the perpendicular between the tangent and the normal. So we can define this as the cross the normal. Okay. And then to connect all of this in terms of what we have in the graphs, we need to define the curvature as, this is the first definition, means that it's tangent, okay, and this is the length. Okay. We can apply this, and using the chain rule we can apply and then we can also apply in terms of cross product, and then divide by should be magnitude cube. At least this summary will be important. From here, once last section will be about how about if we observe every plane of the curve, we can observe P, N, and binomial, right? We can also observe from the plane itself, it can have some twist. If we move the point, we see that the plane seems that it can bend and can twist, and we say that we call it as a torsion. If you learn torsion before in mechanical, same meaning. But if we now learn in terms of a vector, okay. Maybe just an intro, and then we can finish next Tuesday. So if I take in terms of the picture, let me write first from these notes that the curvature this indicates how tight the curve will bend. So if we see this dt over ds here, this telling us how normal plane changes as P moves along C. So when P moves, okay, so when P moves, the T at P will rotate in direction of N. See, P move is bending through the N. Okay. So we have dq of ds over there. So it's tend to be, it's going to be the plane is going to be twisted. Okay, and then a space curve. Let me say a space curve can be twisted out of the oscillating plane and since B is we can say it's the normal to oscillating plane, then this dB over ds this will inform us about how the osculating plane changes. Changes as the P moves. And we can write that dB over ds is equal negative I think not really clear, maybe bigger. Okay. This is the torsion. If you take the dot product for both sides, we can rewrite this as okay, perhaps I will just finish until here.